This continues a set of videos I'm creating looking at past exams, particularly last year's, and sort of doing it as a video format. You should also have available to you online the solutions to everything. One of the big questions often for students is what is going to be expected from me on a final exam. And the 2020 final exam, just as a reminder, I'm sure you're all well aware, is the first exam that we've had during the coronavirus. And so as a result, it was an online exam, which was slightly different than our typical exam. So you'll see some small differences, and these may sort of continue through as we advance through the rest of the course. And ultimately, while it may be slightly different in format, it's still the components are still what is normally expected from you. So I have the first question. Two small spheres, each of mass 100 grams, are connected to a cord of length 2b. B is 1 meter. And it's measured from the center of the spheres, and it's initially at a rest on a horizontal surface at theta equals 0 degrees and time equals t1. A bullet of mass m0 equals 10 grams with a velocity of 400 meters per second hits perpendicular to the cord in the middle, as shown in the figure on the left. As the bullet continues to travel to the right, the cord pulls on the two spheres at time t2. Assume there's no friction or heat generated by the bullet interacting with the cord. Also assume the cord remains in tension, does not stretch and does not break. At time t3 and theta approaching 90 degrees, what is the velocity v of the bullet near contact, and what is theta prime? So this is a particle kinetics problem, and let's break it up into parts. So if I do that, I know kind of that sum of forces in x is equal to 0, but I also know, and that tells me that there's no impulse that's done because it's a relatively short period of time. All of the forces are sort of short time. So if I look at the velocity of the bullet starts at v0, and at the second time, it's going to move to velocity v. And velocity v is the condition at the second point. So if I look at this figure right here, it's going at v. I can calculate v, and that's just momentum balance. m0 v0 equals m0 v plus twice mv, and v is the only unknown, and I get 19.05 meters per second. You're then asked for theta dot, omega, and here it's going to be a force velocity distance. First question was force velocity time, short time. This is a distance. And you have to recognize that the spheres, each of these spheres over here, this one and this one, are going to have a velocity in the direction left to right, but also a rotational direction, which is defined by the half length of the cord, b theta dot. So the initial kinetic energy is all linear, 1/2 m0 v0 squared plus 1/2 m0 v squared, which continues to be straight motion. And then the two other ones, which the two spheres here, which I've identified with the x's, are going to have v squared plus b squared theta dot squared, and then close parent. And so there should be another parentheses right there. And I can say theta dot equals v0 b square root m0 plus 2m equals 87.3 rads per second. So this one is a question that we will always sort of be interested in making sure that you can recognize both particle momentum and particle work energy problems, force velocity time, force velocity distance. And in this case, the real tricky bit is recognizing that when the bullet has hit the center of the cord, it's going to induce a rotational motion. Second problem, is one where AB is pinned to the ground at A, as shown in the diagram. Wheel at point C moves horizontally along the ground. At the instant shown, you have omega AB, which is minus 2.7 k rads per second. So that's clockwise, according to my notation. And alpha AB, which is positive. And you're asked to find omega BC, alpha AB, AC. And you're given particular coordinates for the last two. AB and AC have to be in XY coordinates. So if I want to look at the solution, what I have to do is start breaking it up into the parts. And the first thing I'm going to look at is omega BC. And I know bar of BC has no instantaneous center of zero velocity because if I look at this diagram right here, I have the 2 points, B and C, and the whole thing, and everything is parallel. So if that's the case, then there's no point where these two lines, these two blue lines I just drew, are going to ever intersect. And so therefore bar BC has no instantaneous center of zero velocity. So that's an inspection solution. For AB and XY coordinates, I can do it directly from the various relationships. And this is just broken up into directly into its final parts. AB is omega AB squared, RAB in the minus j direction, alpha AB, RAB minus j, and you end up with minus 6 I minus 23.52 j meters per second squared. AC is going to be a relative velocity expression again, but here I just say AC equals AB plus AC with respect to B plus AC with respect to B, normal and tangential. Add in the component parts, recognize this thing starts from rest, and I have one unknown alpha BC and another unknown AC. So vertical component of AC is 0, so I can say that J is going to equal, or ACJ equals 0, and I can get alpha BC, and I get AC, which is 11.67 I meters per second. The other way I can do it is graphically. I would recommend against it until you're very comfortable with this. And typically I would have solved this maybe a little bit differently. I might have used cross products just because I could draw all of the terms out easier. But if you do this, you can use the law of sines, and from the law of sines, if you have AB and you have AC, then you can calculate AC with respect to B tangential, because AC with respect to B normal is equal to 0. So you have AC, which is equal over sine gamma equals AB over sine delta, and you'll get the same result, 11.66 I. If you don't, you're in trouble. Generally, if you look at these problems, particularly part A, you're seeing a problem that you have to do inspection. And it's really important as you go through these diagrams. For example, when I created this slide initially, I didn't have the figure right here. But it's really important that in order to get a handle on what's happening, you draw the figures out, look at where the motion is, and then you draw draw your conclusions. The math is not enough, the physics is not enough. It's a combination of the two. Third question, long thin rod AB, mass 4 kilograms, length of 7 meters, released from rest of the position shown. As the rod falls, point B slides freely along the floor with no friction. Draw the rod's free body diagram and determine its angular acceleration immediately after it is released. G is 9.81 meters per second squared and 60 degrees. So there's all that information. You have the free body diagram right there because there's only one point of contact. This thing is only touching the ground here, so that's force at B. You have weight acting downward, and those are the only two forces determining this. This is one of those tough problems to visualize and to get a handle on, not because it's a hard problem, but it makes it, it's one that you try to imagine more is there than there actually is. And you want more, but there's nothing else there. And you have to think about it, and once you get comfortable drawing these free body diagrams, and this is crucial in the course, you get better handles on what's happening here. So if you do the sum of forces in x, you get 0 for AGX, because there's no x forces, and acceleration in x is equal to 0. acceleration in y, you have the two forces there, and you have the acceleration g in the y direction. So finally, you have sum of moments about b, g, which is ig alpha, and you can calculate from that a relationship between the force at b and the angular acceleration. So here, this is just force at b, distance over which its distance, radial distance between g, and on the other side you have 1/12 ml squared, which is a number or an ig that you're very familiar with at this point. You can calculate all of the accelerations, and you get agy is minus 1.7 alpha. Substitute all of these equations in. 1, 2, 3. You go 1, 2, 3, and 4. Excuse me. And if you do, you end up with alpha equals 2.4 rads per second squared. There's often, the typical sort of error is that the sum of forces equals 0, or in this case, sum of forces in x equals 0, sum of forces in y don't equal 0. Or to do sum of moments about b. Typically, you want the unknown force as the force which you calculate the moment, and that makes it easier. And you kind of think about it, but there's a tendency here to make a trivial solution and lose out on all the marks. This is a very complex one to read, and I'm going to spend some time on this. Two wheels are connected by a link at their center and sit initially at rest, and that's at location A right here, on a 20-degree incline. So there's the incline. A rope is wound tightly around the hub at wheel 1. There's wheel 1, anchored at the wall at the top, and you can see the anchoring occurs right there. Two wheels are released and allowed to roll down the incline at location B, where the rope has unwound by 5 meters. So location A to location B. So this is just moved down. Wheel 2 rolls without slip. So this is useful information. There you go, rolls without slip. While wheel 1 must roll with slip because of the way the rope is attached. Data for the two wheels inclined is given below. Ignore the mass of the link in your analysis. So the nice thing about that is that it gets rid of an IG term for the rod. So wheel 1 is 30 kilograms, R1 1.2 meters, R hub is 0.8 meters, K1 the radius of gyration 0.75 meters. Wheel 2 40 kilograms, R2 1.9 meters, and K2 the radius of gyration 1.3 meters. The incline has a coefficient of static friction of 0.1, mu k equals as defined below, and theta equals 20 degrees. Draw the two free body diagrams for the two wheels, indicate the location of the instantaneous center of zero velocity on each wheel. If mu k equals 0, determine the total kinetic energy of the two wheels, determine the velocity v sub g of the whole system. Mu k equals 0.05, and the normal force between the floor and the wall is given to you as force sub n1 is equal to 274 newtons. Determine the final angular velocities of the two wheels and the final angular accelerations of the two wheels at B. So here's the free body diagram. Both wheels rotate clockwise by observation. We kind of expect that that's the direction they'll go down the rope or down the ramp. The IC is for wheel 1 is at the point of contact. The IC for wheel 2 is at the incline surface. And so that's kind of what you're thinking about at that point. Beta is the angle between the incline surface and F link. And so you have all of this information. Force of friction R1 is mu k F N1. FR2 is less than or equal to mu sub S Fn2. There we go. Kinematics, those show you the instantaneous centers at the 2 points. So this is wheel 1 right here, and that's wheel 2. If mu k equals 0, determine the total kinetic energy of the wheels. So typically, if I solve these problems, I use conservation of energy, TA plus VA equals TB plus VB. Both will give the same result. The important thing is, one, at the beginning, there is no motion, so the kinetic energy at A is 0. At B, it's at the low point, and that's going to be my defined datum, and so VB is equal to 0. Gravity is the only potential energy. So VA equals TB, whether you write it as a work term or whether you write it as a work energy, gravity, okay? So if I put in all the terms, I have at the top, I have gravitational potential energy, which is this term right here. I have linear and rotational energy for wheel 1, linear and rotational energy for wheel 2. And I know where the point of no slip is, and I can give that as Vg over R0 and Vg over R2 for the two wheels. And so TB equals M1 plus Mg, G sine theta delta S, and I substitute all the terms, and I can say, I don't have to solve for this at this point. All I have to do is solve for this, and I know where the height is. So that's just going to be 1,174 joules. Now, to determine the velocity, the total velocity of the entire system, remember that this system is sort of, they're both attached at the center of the wheel, and so they're moving down at the same rate. I can take the total kinetic energy and divide that by all of the other terms, and I will get that, because of my coordinate system, 4.52 meters per second down the ramp. And that's using the sign convention that I was given. That's why it's positive. Now, if mu k equals 0 and the normal force between the floor and the wheel is Fn1 equals 274 newtons, I don't have to do as much work because I'm given something, but something does change. Find the two angular velocities, find the two angular accelerations. So the only thing that's changed in my expression is this one right here. And so all of the rest of the terms remain the same. And the instantaneous center is, at the rope. The wheel slips at the surface, and the wheel is going to slip at the surface and travels half the distance delta S. And that's the tricky bit in this particular problem. So you have TA plus VA plus work 1 to 2 from friction is equal to TB plus VB. So that's, and the work of kinetic friction is always going to be negative. So it's always going to oppose motion. So you're going to go travel in one direction, and you'll have force of friction in this direction, and this is your direction of motion, and so you end up with a negative value. Total distance traveled is going to be 2.5 meters. You can calculate Vg, omega 1, omega 2, and you can use kinematics in this case, and that's how you're going to get it, because you know that what the initial velocity is, what the final velocity is, and you know the arc distance traveled, the distance traveled, or angular distance. So you have this. No, you don't have that. That's your unknown. And you have this, which is delta theta. Same thing for omega 2. Those two terms go away, and you get alpha 1 equals 2.48 rads per second squared, and alpha 2 equals 1.04 rads per second squared. This is a very complex problem, and it's one that you should spend a lot of time sort of thinking about and trying to figure out how comfortable you are with some of the physical assumptions that were made in order to solve it. You need to recognize where the slip, no slip points are and how to work from them. I think this is question 5. Drum with mass equals 100 kilograms, radius 1 meter, radius of gyration of 0.8 meters, sits at the rest on the ground. Coefficients of friction between the drum and the ground are mu sub s equals 0.4, mu sub k equals 0.3. Drum is struck by a constant impact force of 1,000 newtons at a distance of 1.5 meters above the ground for 0.01 second. Use the given coordinate systems and sign conventions. Prove the drum will roll without slip during the impact. Find the angular velocity, omega k, after impact. Calculate the velocity of the center of mass immediately after impact. After applying a surface treatment, you change the coefficient of friction to mu sub s 0.04 and 0.03. So you dropped it by about 10 times. Determine the new angular velocity immediately after impact. So that's my free body diagram. That's where I'm just going to start. You will notice that I have done one thing in this problem, which is define a positive clockwise rotation, which is opposite to the convention. Assume no slip. Solve through some forces in x, some of moments about g, and I'll get alpha is 9.15 rads per second and force of friction, which equals 85 newtons. Check the assumption, force S max, 392.4 newtons. And after that, the angular velocity, I'm going to assume starts from rest. It's occurring over some time, and I solve through and I get omega 2, which is 0.091 rads per second. Calculate the velocity of the drum's center of mass immediately after the impact. Velocity sub g, because it's not slipping, is r omega 2. Or from linear momentum, both of those would get me the same result of 0.091 rads per second, meters per second. Check our assumptions. Force S max is 39.2, rolls without slip because force friction is equal to 29.4 newtons. So it works out very well. And the new angular velocity is 0.083 rads per second. Now, one of the final things that we often cover, or we always cover, is vibrations. And here's a kind of interesting problem. You have 4 springs with a constant, or a spring constant of 135 newtons per meter. G again is defined downward. Natural frequency of the 11 kilogram cart, mass of the cart is given, K of the spring is given. And if you do this, you can say, well, I have a free body diagram that consists of minus 2kx minus 2kx. I have xy there. K equals 135 newtons meters. So I want this to end up as a positive. So that's why I've defined this as a negative sort of direction. X double dot plus 4k over m, x equals 0. And I get the natural frequency, which is really this term right here. This is my k over m term. It becomes 4k over m because that's the real spring constant for the system. And frequency of this is omega n over 2 pi, which is 1 over 2 pi 4k over m. And so F is equal to 1 over pi k over m, and I get 7 hertz or 1.12 hertz. This is a slightly more complex problem. It's not terribly complex. What's the natural frequency if C1 equals 0, if C1 equals 75 newton second meters? Is the system critically damped, overdamped, and underdamped? Sketch the vertical displacement as a function of time if the mass is given as an initial displacement of 1.2 meters and then released at time equals 0. So I got x at 0 and x prime at 0. So I can write all the terms out. I have static plus this, so that's my static equilibrium term. I'll then have my double dot plus 2cy dot plus ky equals 0. 2c because there's 2 of these dampers in place. So my governing equation is in this form right here, and omega n of the system is square root k over m. My critical damping coefficient is 2m omega n, and I have omega n, which is 1.25 rads per second, and critical damping coefficient 80 kilograms per second. Each of these is 75. I've got 2 of them, so the system is overdamped. Again, looking at the coordinate system, I've defined positive downward. So I've given two points. X is 0 is 1.2 meters. X dot equals 0 meters per second. I have a solution that takes the form for overdamped AE to lambda 1t plus BE lambda 2t. Solve through using the definitions in the book. Lambda 1 is equal to minus 0.362, lambda 2 minus 4.33. Substitute the terms in and substitute all the expressions, and I'll have something that is a decaying exponential that looks something like this. And so that's after 10 seconds. I use Wolfram alpha to plot this and then just copy the plot over. In terms of conclusions, covers all the rigid body and vibration component, less emphasis on particles because we've covered those by quiz 1 and midterm 1. And this is a lot of material. In essence, this is the second half of the course. In large part, there is always a problem that will relate to the particle component. So it's really covering the entire book, and you're looking at 700 some odd pages. It's a lot of material, and just make sure that you keep up with it so that you're comfortable with it. Thank you, and we'll talk.